In this series of lectures, we're going to focus on how we can sketch the graph of a polynomial. And when we're doing that, there are really three things that we're going to focus on, three attributes that we're going to focus on: the end behavior, the roots, and the multiplicity. All right, now in this lecture, we're going to start talking about the end behavior. And the idea here is that we're interested in the behavior of the polynomial in two different places, right? First, we're interested in what it's doing way out here on the edges as the x values get either really big or really small, really large negative numbers. And then we're going to be interested in kind of what's going on in here in the middle. End behavior is the outer edges, right? This is the concept we're going to use to decide what's going on kind of at the extremes of the graph. Roots and multiplicity, we're going to talk about those in later lectures. That's what's going to tell us what's going on in the middle. All right, so end behavior, there are really four cases that we need to be aware of. And that's going to make this lecture a little longer than usual, so I should just kind of bear with me a little bit, because we need to talk about each of these four cases and see what's going on in each one. So to illustrate the first case, I want to take a look at this polynomial. And remember, when we talk about the end behavior, what I want to know is, what is the graph of the function doing as the x values get really large? So you can see I picked some really increasingly large x values here. And I want to calculate the functional values at these numbers. And to do that, I'm really going to break this down. I want to look at the individual pieces, the individual terms of the polynomial. So when x is 1, x squared is 1, 10x is 10, 100 is 100. X squared plus 10x minus 100 is negative 89. So you see how I'm filling these in, right? So if you like, you can pause the presentation here, take a second, see if you can fill those numbers in yourself, and see if you can spot the pattern, right? See what's going on in those final y values. All right, so the numbers I'm getting here, let's see, this would be 10 squared, that's 100. 10 times 10 is 100. And the polynomial, the y value is 100. Let's see, down here I get 10,000, 1,000, 100, and this comes out to 10, 9. Finally, this is 1,000,000, 10,000, 100, and the functional value is 1,009,900. So first I want you to look at the y values. And I think it's pretty clear what they're doing. They're getting big, right? They started out down here, and then they went up and dramatically up. So you can see the behavior of this graph as x gets really large is it's increasing without bound. It's going off to infinity. And the language that we use to describe this is, I would say, the graph increases to the right. All right, now another thing I want you to notice here, right? Compare the individual columns. This is why I wanted to work each of these out separately. This middle column and the 100 column, they're really not having much of an impact in the long run. My x squared term it contributed 10,000, and the answer and the final y value was really pretty close to 10,000. Over here on the 1,000 row, the x squared term contributed 1,000,000, and the y value, well, it was even closer to 1,000,000. The 10x and the 100 term become increasingly irrelevant as x gets large. So really, when I'm focusing on the end behavior, it really is just this first term, the leading term, that's determining what this final behavior is. All right, so with that in mind, I want to kind of rethink this exercise, but now we want to think about what's happening as x gets really negative. So instead of 1, 10, 100, let's do -1, -10, -100, and -1,000. Right? Well, the x squared numbers all stay the same. There's still 100, 10,000, and a million. Now, these 10x numbers change, right? These are going to become negative. So there's going to be this small drop off in these y values. But again, and if you go ahead and work these numbers out, you'll see the effect that these numbers have on the final result is pretty minimal. The final numbers are still really close to 10,000 and a million as x gets very, very negative. So the behavior here is going to be very similar. The y values stay positive and get large. So I would use the same language here. I would say that the graph also increases to the left. We say increases. Sometimes we'll say rises. Right? Rises is another word that's commonly used, so you'll see both of those. All right. So this is my first case. All right. Now let's look at another one. Let's look at case 2. You notice I have made a very small change. Right? I've made a very small change to my polynomial. All I've done is I've slipped a minus sign out in front. I've changed the leading coefficient from positive to negative. All right, so try doing the same thing now. You see, I filled my table in again, and I've explicitly put that minus sign here. All right, so try working out the table again, see what you come up with. Then we'll talk about what the y values do in this case. All right, so here what I'm seeing, and I'm just going to jump to the final results. I'm seeing negative 91, negative 100, negative 9,100, negative 990,100. And my x squared numbers, right, these were minus 1, minus 100, minus 10,000, and minus 1 million. So we're seeing the same behavior, right? This leading term is the one that is driving our final result, and now we're getting numbers that are negative and increasingly negative. So you see the end behavior of this thing. And the way I would describe this is I would say the graph falls to the right. All right, again, if you repeat the exercise, right, if we put negative numbers in here for x, these numbers don't change. Just like they didn't change on the previous one, because when we square negative 1, it becomes positive 1. When we square negative 10, it becomes positive 10, and so on. So my answers are going to be very similar. They're going to be dropping off this way. So there is my end behavior. I would say this graph also falls to the left. All right, so there are actually two things. Hopefully you're starting to see this now. There are actually two things that are driving this end behavior. The first is the exponent, right? Because the exponent is even, it doesn't matter if we put a positive or a negative number in there for x, we get the same result. And this leading coefficient, the sign of the leading coefficient matters, because that determines whether or not the final value for that term is either positive or negative. All right, let's try another one here. Right, same situation, right? And I'm pretty well convinced now that that leading term is going to be what's driving this. But you can go ahead and fill these numbers in if you like. You can pause it, do your own calculations. Notice the key difference here is I've changed the exponent from a 2 to a 3. So now our exponent is odd. And I want to see what that behavior is. All right, well, again, if you do these calculations, you're going to get negative 89, positive 1,000, positive 1,900,000, and positive, what would this be, 1 trillion? 9,900. All right, so it's the same thing, right? We're seeing the exact same behavior. The numbers start off here and then increase even more quickly. So this also increases or rises, whichever word you want to use, to the right. Now here the situation is a little different, right? If we let the x's be negative, then this leading coefficient, again, let's just focus on the leading coefficient, right? Because I'm claiming that that is all that I really care about. So if I start putting really big negative numbers in there, if I do -1, -10, and so on, the leading coefficient will be -1. -10 to the third is -1,000. -100 to the third is 1 and 6 zeros. That's -1,000,000. And -1,000, that would be -1 followed by 9 zeros. So we're seeing a similar behavior now, right? We're getting negative numbers and it's dropping off quickly. So this graph falls to the left. All right, so that was our third case. All right, case 3. Now we're looking at a case where we have an odd exponent and a positive leading coefficient. And there's one more case to consider, right? The minus sign got left off here. So now there's one more case to consider, right? The negative sign got left off. The negative sign is here. Right, now we have a negative leading coefficient. And this is how I do that. I'm going to summarize all this on the next slide. And if you're really into memorizing rules and results, that's fine. Go ahead and memorize all these 4 cases. But this is how I answer these questions in practice. I say to myself, if I put a really big positive number in for x, if I put 1,000,000 in there, 10 to the 6th, what do I get from this leading term? Because that's the one that's driving the show. I get -10 to the 6th to the 3rd. That's -10 to the 18th. It is a massively large negative number. That tells me the end behavior. It's falling to the right. Then if I went to the other side, I do the same thing. I ask myself, well, what if I put a massively large negative number, say -10 to the 6th, in for x? All right, well, if I raise that to the 3rd power, I get -10 to the 18th, which is +10 to the 18th. It's a really big positive number. Now I know my end behavior in this direction. It rises to the left, right? So, as promised, this side, it summarizes everything we've talked about. These are the 4 cases. The 2 here where n is odd, and the 2 here where n is even. And like I said, if you like memorizing things, go ahead and memorize all 4 of these cases, have them on your fingertips. For myself, I just drop a really big test number in to my specific polynomial and see what I get out. If I get a really big positive number, I'm rising. If I get a really big negative number, the graph of the polynomial is falling.